In this video, we solve problem 4.6.8 from Nagle's Fundamentals of Differential Equations, 7th edition. We're asked to find the general solution of the differential equation using variation of parameters. And I will just note that variation of parameters is the only method that we can use to find y sub p in this case, because the right-hand side is not an exponential function, a sine or cosine function, or a polynomial function, or a finite sum or product of those. This is a cosecant squared. Since it's a cosecant squared, we have to use variation of parameters. But notice that it is a non-homogeneous differential equation when all the y's are over here and all the functions of the independent variable, in this case t, are over here. The right-hand side is not 0. So that means y is equal to y sub c, that's the solution to the corresponding homogeneous problem, plus y sub p, that is a particular solution, which we'll find using variation of parameters. But in order to find y sub p, we need to solve the homogeneous problem first. So let's do that. Got y double prime plus y equals 0. And since this differential equation has constant coefficients, we're going to let y equal e to the mx. Now it's second order, so we just need a y prime and a y double prime, and then we'll substitute into the dE. Excuse me. The derivative of e to the mx is e to the mx times the derivative of the inside. The derivative of a constant times x is just the constant. So we multiply by an m. If you take the derivative, again, you're going to get another m because you're just going to bring your constant down and multiply by the derivative of e to the mx. Derivative of e to the mx is e to the mx times the derivative of the inside, which gives us another m. So we've got an m squared there. Now, if we substitute into the differential equation, we end up with y double prime, which given the form of our solution would be m squared e to the mx plus y, which is e to the mx, and we want that to be 0. Well, that's equivalent to saying that this must be 0. And the exponential is never 0, so we must have m squared equals 1, or m squared plus 1 equals 0. So that's a characteristic equation. This is the equation that must be satisfied by m if y equals e to the mx is to satisfy that equation. If we solve this for m by subtracting 1 from both sides and then taking the square root, don't forget your plus or minus. You have m1 and m2 are equal to plus or minus the square root of -1, which is just an I. So I can think of that as 0 plus or minus 1i, oops, not t, I. So alpha, that's the real part of that, or those complex conjugate roots, is 0, and the imaginary part is just 1, plus or minus 1, but we'll think of beta there as 1. So these will tell us the forms of y1 and y2. Since we had complex conjugate roots, y1 is e to the alpha x times cosine of beta x, and y2 is e to the alpha x times sine of beta x, where alpha and beta are the real and imaginary parts of that complex conjugate pair. Well, the beta is the absolute value of the imaginary parts. In our case, alpha is 0, so this is e to the 0x, which is 1, times cosine of beta x. Beta is 1, so this is cosine of x. And y2 looks just like it, but instead of a cosine, you have a sine. So our two solutions are cosine of x and sine of x. So y sub c is c1 y1 plus c2 y2. All right. Now we want to go back to the original differential equation, which was this. Oops, it said cosecant squared t, didn't it? So I guess I need t's everywhere. So this should be e to the mt. Okay, sorry about that. Change all your x's to t's. So we've got cosine of t and sine of t. All right. The right-hand side is 1 over sine squared of t. So we can't use the method of undetermined coefficients. So we're going to use variation of parameters. We're going to let y sub p equal u1 y1 plus u2 y2, where u1 and u2 are not constants. Then, by the derivation we did in class for variation of parameters, we saw that u1 prime had to equal w over w, and u2 prime had to equal w2 over w, where w is the Wronskian of y1 and y2. Now, once you choose your y1 and y2, you have to be consistent with that. I've chosen y1 equals cosine of t and y2 equals sine of t. If you chose it in the reverse order, that's fine. Your w's may be different, but your answer at the end will be the same. It's logically equivalent. Doesn't really matter which one we call y1 and which one we call y2. Derivative of cosine of t is negative sine of t. The derivative of sine of t is cosine of t. So we're going to multiply across this diagonal and that diagonal and subtract. So we'll have cosine squared t minus a negative. That's going to be plus sine squared t. Sine squared plus cosine squared is 1. So we've got our w. w1 comes from replacing the first column with 0 and f of t. Now, f of t has to be the right-hand side of this differential equation when the leading coefficient is 1. Now, this time, the leading coefficient is already 1, so f of t is the cosecant squared of t. But if there wasn't a 1 there, we'd have to divide by that function. So I have 0 and cosecant squared t, and we leave the second column alone. And then we evaluate this determinant. You get 0 minus this. So that's going to be negative, and you've got a sine of t, and cosecant squared is 1 over sine squared of t. So one of those will reduce. You have 1 over sine of t that's left, negative 1 over sine of t. So you're going to have negative 1 over sine of t, which is a negative cosecant of t, or w1. And w2 comes from taking our Wronskian and replacing the second column with 0 and f of t. Remember, these determinants come from Cramer's rule. We have this times this minus that times that. So cosine of t times 1 over sine squared t. And you can write that as cosecant squared t, but I would rather write it as cosine of t over sine squared t. I think that'll be easier to anti-differentiate, or at least rearrange. So that is our w2. All right. So we know that u1 prime and u2 prime have this form where these are our w's. Now let's find u1 prime and u2 prime. So u1 prime is w1 over w. So it's negative cosecant of t divided by 1. So that means u1 is the antiderivative of negative cosecant of t. Well, the antiderivative of cosecant of t is a negative 1 times a logarithm. The negative times the negative will make it positive. So it'll be the logarithm of the absolute value of cosecant of t plus cotangent of t, plus a constant of integration. And we're going to choose that constant of integration to be 0. And then u2 prime is w2 over w. And then we'll compute the antiderivative of that to get u2 by itself. So we've got cosine of t over sine squared t over 1. Now, I don't have a rule for that. I could use a u substitution where u is sine of t if I'm wanting to anti-differentiate that. There's another way we could do this. We could split this up as cosine of t over sine of t times 1 over sine of t. If you distribute straight across, you see you've got 1 cosine over sine squared, same thing. Well, 1 over sine of t is cosecant, and cosine over sine of t is cotangent. So this is actually cotangent times cosecant, and we're going to write it in the reverse order, cosecant times cotangent, because that's how we're used to seeing it. That's u2 prime. So u2 is the antiderivative of that. And the antiderivative of cosecant of t times cotangent of t is negative cosecant of t, plus a constant. And we'll choose that constant to be 0 because we're going to multiply u2 by y2, and we don't need a constant times y2 as part of our y sub p. Okay, so we've got u1 and u2, and that's enough to help us write down our y sub p. It's u1 y1 plus u2 y2, and u1 was this logarithmic function. And we want to multiply by y1. Remember, our y1 was right here. That was cosine of t. Our y2 was sine of t. So this is this. We're going to take this function and multiply by cosine of t. Over here, we're going to take u2, which is this guy right here, negative cosecant of t. And we're going to multiply it by y2. Negative cosecant of t is 1 over sine of t. And y2 is sine of t. The signs reduce, and you get -1. And so y sub p is equal to this, which is just this plus a -1, or you can just subtract 1. Okay, so we've got our y sub p, we've got our y sub c. We'll just put those two pieces together to write down the general solution. So you have c1 cosine of t plus c2 sine of t plus cosine of t times the natural log of cosecant of t plus cotangent of t in absolute value, -1. And this would work on an interval where sine of t is non-zero, and we did not have an initial condition. So let's say on some interval of the form n pi to n plus 1 pi, where n is an integer, because we can't have a sine of t in the denominator here, because then we would be dividing by 0. Also, this is a 1 over sine of t and a 1 over, or a cosine of t over sine of t, so 1 plus cosine also should not be 0. So cosine can't equal -1. So that means we can't be dealing with any, well, cosine is equal to -1 at pi. So, so we can't have that pi or 3 pi, or, well, I guess we would have to be very, or even more specific than this to make sure that this is well defined. I'm not going to get into that too much. Something like this, though, we need to consider that we can't take the logarithm of 0. Of course, we can't divide by 0 in order to find the interval of existence. But this is sufficient for your answer in MyLab Math. I think this is a good discussion to have, but we can have that type of discussion in class.